Independent events. Two events are independent if the probability of occurrence of one event is not affected by the other. If A and B are independent events, then the probability of A intersection B, the probability that both events will happen, is equal to the probability of A times the probability of B. Independent events versus dependent events. So I will show you two examples. They are somewhat similar, but at the same time they are different because one is an independent event and the other is a dependent event. This is our experiment. We shall select two marbles from an urn or from a jar. Okay, I think an urn is not the right container for this. It should be selecting two marbles from a jar. Okay, so inside your jar you have 5 marbles that are blue, 3 are red, and 2 are white. Now we shall select 2 marbles one at a time with replacement. So what that means is we will select 1 marble and then we will return that marble into the jar. A is the event of selecting a white marble. B is the event of selecting a blue marble. Find P of A intersection B. So P of A, the probability of getting or selecting a white marble is 1 over 5. Why 1 over 5? Because you have 2 white marbles and your sample space contains 10 marbles. So it's going to be 2 over 10 or 1 over 5. What is the probability of selecting a blue marble? Okay, so we will return the first marble into the jar. So what now is the probability of getting a blue marble? Well, you have 5 blue marbles and the size of the sample space is 10. So it's going to be 5 over 10 or 1/2. So the probability of selecting a white marble then a blue marble is equal to 1 over 5 times 1 over 10. No, 1 over 2 I mean, which is 1 over 10. Now this is where the independent or dependent events makes a difference. The same experiment, we will select 2 marbles from a jar, but this time we shall do it without replacement. We shall not return the first marble that we took from the jar. Again, we have 5 blue marbles, 3 red marbles, and 2 white marbles. A is the event of selecting a white marble. B is the event of selecting a blue marble. Find the probability of A intersection B. So A is the first marble that we chose. Okay, A is the event of selecting a white marble and B is the event of selecting a blue marble. Well, going back to our slides on conditional probability, the probability of getting a B or getting a blue marble, given that in the first stage of your experiment, you selected a white marble. Okay, so that is how we interpret this. The event of B given A. The event of getting a blue marble in the second selection, given that in the first selection you chose A. It is equal to this. The probability of A intersection B divided by the probability of A. Now solving for P of A intersection B, okay, this is just cross multiplication. It is equal to the probability of B given A times the probability of A. So there's a difference here, okay? If they are independent events, P of A intersection B is just P of A times P of B. but not so when they are dependent events. When they are dependent events, P of A intersection B is equal to P of B given A times P of A. But also you can write it in the following way. P of A given B times P of B. This one, dependent events, this one takes place when our selection is done without replacement. So just exactly what does that do to our experiment? Well, if you are going to do it without replacement, the sample space in the second stage of your experiment is fewer now. It's fewer. It's smaller now. Okay, so that is the main difference between dependent events and independent events. That's what dependent events do to the sample space. Okay. Well, given that you selected one white marble from the sample space, the probability of getting a blue marble in the next selection is 5/9. Where did 5 come from? 5 comes from the fact that you have 5 blue marbles. Why 9? Why 9 and why not 10? Because the sample space had been reduced by 1. That's why it's 5/9. Now, in the first stage of your experiment, the probability of getting a white marble is 2/10, which is 1/5. So the probability of A intersection B, okay, using this, is equal to 5/9 times 1/5. Okay, 5 divided by 5 is 1, so it's 1/9. So let us compare the two. Two experiments somewhat similar, but at the same time they are different because one is done with replacement and the other one is done without replacement. Look at the difference. The probability of A intersection B is 1/10. That is for the experiment with replacement. P of A times P of B. The events are independent, but not so when the experiment is done without replacement. P of A intersection B is equal to 1/9. So they are not equal. This is our experiment. We shall draw 2 cards, one after another from a deck with replacement. So this is going to be an example of independent events. A is the event when a red card is selected. And you have 26 red cards. So P of A is 26/52, which is equal to 1/2. B is the event when a red face card is selected. You have 6 red face card. 6/52. 2 is a common factor. So 2 divided by 2 is 1. So we are left with 3 divided by 26. A intersection B is the event when the first card that is selected is a red card. The second card is a red face card. That is how you interpret this. So what is P intersection B? It is equal to P of A times P of B. It is equal to 1/2 times 3/26 or 3/52. Now we shall do it again, but this time without replacement. So P of A intersection B is equal to P of A times P of B given A. Given that you already selected A, or A already happened. So the probability of getting a red card is also 1/2. But this one is done without replacement. So since you already selected one card, your sample space had been reduced by 1. And so the probability of B given A is 6. You have 6 red face cards divided by 51. Okay? Divided by 51, not by 52, but 51. And so their product is 3/51. So let us compare it with the experiment when it is done with replacement. So this experiment is an example of independent events. Look at the probability. It's equal to 3/52. For dependent events, and that happens with conditional probabilities, the probability of A intersection B is 3/51.